All right, let's go and get started. And let's try this one again. Let's go with take two. All right. Okay. All right. First off, let's deal with the simple stuff. So you all have your homework 4 due on Monday. I'm going to remind you, of course, everybody's almost done with it, right? In all seriousness, though, does anybody have any questions? No, I fully predict that. But it is going to creep up on you if you wait. I mean, if you wait until the 19th to start that, it's not going to be pretty. I mean, it's going to be a lot of work. Homework's due on the 20th.
That's still a long time.
All right. Okay, now, let's talk about the exam. So we were at a dead even tie last time we talked about this. I don't want to sit here and have another 20 minutes of discussion on the exam, so we're going to keep this simple. Have you all found the nearest octagon facility or mixed martial arts facility and worked out your decision as to whether or not you want to do the exam on Wednesday or Friday? And what?
Friday.
All right, hold on. Just so we're clear. Are we doing the exam on Friday? Are we doing the exam on Wednesday? All right. I will send an email. We are doing the exam on Friday. We are not moving the homework. The homework is due on Monday. No. But you're graduating. No, you'll still be here. Now, I don't give A's, you earn A's. That's the thing. What's that?
I'm probably not coming. Oh, a take-home exam? That's what I heard.
You have an exam on Friday.
Friday, the day of concrete exam. I didn't think we had exams.
No. Nope, we press on. No. We got stuff to cover, and we lost some time last time with the slab. We're doing take 2 on that slab design. All right. Semblance of order. So are we clear that exam 1 is moving to Friday?
Yeah, take home.
We. I do not accept amendments to the motion. You do not follow Robert's Rules of Order. I mean, you had your chance to insert a point of inquiry, and you missed it. That motion is out of order at this time. All right. Homework's due on Monday. Exams on Friday. Everybody good? All right. We are going to press on with this slab, though. We are going to finish it. All right, here's our slab. So we have been working on the design of a one-way slab. Now the span length is 10 feet. Let's be clear. When I say span length for a slab, that's for the slab. For girders, that's the girder spacing, right? Because the slab spans the girders. That's how far it is between the girders, or beams, whatever you want to call it. The slab is to be constructed of normal weight concrete with a compressive strength of 4,000 psi. The rebar is grade 60. We have a live load of 200 psf. So this is some serious live load on this element. Now the only dead load is the self weight of the slab. We don't have a superimposed dead load on the slab. We could, but we don't need to worry about it. Everybody good? Yes, sir. Oh, I have it right here, and I just. Okay. Now let's review where we left off and where we're headed with our calcs. So let me full screen that. Full screen. Okay. So here's our slab. Again, that image regarding the slab configuration. The span length for the slab is the spacing for the beams. We're selecting both the main reinforcement, which goes from beam to beam in this direction, and we're also going to be selecting the temperature reinforcement, which goes in the opposite direction. Now, we're going to assume that the depth is the height minus 1 inch to account for some cover. If your bar size gets pretty big for your slab, you might need to iterate that, but it's just something you can just check at the end. If the bar size is a little bit larger, just take your D and trim it down a little bit and iterate. Okay. So next thing, we have to compute our factored moments. We have a beam width of 12 inches because when you're doing a slab design, you essentially just say, all right, let's just design a 12-inch strip, and then let's just design that reinforcement everywhere. In other words, whatever reinforcement I select for that 12-inch strip, just repeat that across the entire slab because that's really what's going on. The slab is 6 inches thick. According to minimum thickness requirements, we're just going to design for the minimum thickness. And our effective depth is h-1, which is 5 inches. So we say, all right, the first thing we need to do is we need the self-weight of the slab, which for that strip is just gamma BH, the unit weight of concrete times the area. So we say, all right, we got 0.15 kips per cubic foot, and then we say the area is 12 by 6 inches. Units gives us an issue, so we got to convert, plug and chug, and you get 0.075 kips per foot. Again, let's be clear. These loads and these moments are going to be low because we're talking about low spans and we're talking about very slender elements. So don't freak out when you're doing a slab design and you get a moment that's like 4 foot kips. Like that's normal for a slab. Okay. That is the self-weight. We also have the superimposed live load, which is really easy because it's just the pressure load times 12 inches or 1 foot. So it's really just taking kips per square foot and turning it into kips per foot. It's pretty simple. So we have a pretty hefty live load on this. We have 200 pounds per square foot. So this slab's going to see a lot of load. All right, sound good? Say, all right, after we've got our live load and dead load, we can factor them. 1.2 dead plus 1.6 live will give us a factored load of 0.41 kips per foot. Take that, WL squared over 8. So that's where we left off last time. Does anybody have any questions about that so far? Everybody okay with that? Okay. All right, so here's where we're at so far. Now you tell me, if we have our factored moment, which that's step 1, what's step 2? You tell me. Say it again. Compute MM by doing what? Assuming phi. So this will be something that ultimately you should go and check in the end. So we're going to say compute required MN by assuming phi. Okay, so we have MN required is MU over phi, which is 5.125, bless you, foot kips over 0.9. What does that give you? 5.69, you said? Like that? Now, that's in foot kips. I'm ultimately going to take that moment and I'm going to say, all right, I need to start combining that with a bunch of FC primes and beam dimensions that are in inches. So I'm going to go ahead and convert that to inch kips by doing what? Multiplying by 12. You don't divide by 12, you multiply. So what is this times 12? There we go. Coffee's starting to kick in, right? All right. Sound good? All right. Now this next one, the calculation's a little involved. Again, essentially what we're doing for this problem and in slab design in general is we are designing a beam with a known cross-section. We know how wide it is. We know how thick it is. So all we need to do is solve for rho. So again, no 0.18 FC prime over Fy. This beam, we know what the beam looks like. So our rho calc is a little more complicated. So compute required rho. So let's see. I'm not that good. Actually, hold on. No, hold on. Let's see if I can do it. No, I didn't actually. I didn't. Let's see. Did I get that right? All right. I'll take my $5. All right, help me out. 0.85 times FC prime. What's FC prime? All right, there we go. All right, and then 60 KSI, right? All right, look, I think I can fit all this right here, so. All right, so 1 minus, I'm gonna try and be neat, but I'm gonna try and squinch it a little bit as well. 1 minus, okay, on the bottom. Now, is everybody making fun of the like squinching and all that, the word I'm using? 4 KSI. What's B? In slab design, that's always the same value. 12 inches. Because that's a good question, because we are designing a 1-foot strip, and then just whatever reinforcement we get, we're just going to repeat that. So we're all like, we could say it's 10 inches and then just repeat that. It's just easier from a unit standpoint and a convention standpoint to just say, let's just go with 12. D is 5 squared and then 2 times, there you go. All right, now, you got to get those calculators working. Yes, sir. Is what? Well, the only way that what you're talking about could really happen is if you've got a beam going like this and then a beam going like that. You know what I mean? Because then it's not like this. You know what I mean? Where it's, like that. And what's that? That's what I was about to say. Then it's not that's not a simple design altogether because the span length is changing from dimension to dimension. I'd argue that unfortunately, I'd argue that the most accurate way to go about that would be to design each strip. Okay. Or you could say, all right, let's just design for the longest strip and repeat that reinforcement. But you got to be careful because if you throw a bunch of rebar into that long strip and then say, all right, I'm going to throw the same amount into that short strip, well, you might over-reinforce the short strip. Do you see what I mean? You just got to be careful. And if you've got a situation like that, then there is no simple answer. You just got to go through and check it out. Yes, sir.
Somewhat off topic, but the thermal reinforcement, the bars,
The temperature, yeah, temperature steel, yes.
I mean, if the slab's in an environment where it's not going to, the temperature's not going to fluctuate a lot.
I would still incorporate it for things like shrinkage, for things like creep, and what have you. I think just over time you're going to get cracking. It may not be due to temperature. It may be due to other material-related phenomenon. I mean, over time, the moisture content in the concrete might change. That's going to change the properties of the concrete altogether, and that can cause cracking. So, honestly, regardless of if I was in Miami and it's always going to be hot, or I'm still going to throw it in there. So, does that answer your question? That's a good point, though. I mean, maybe you could argue that in a place like this, where temperature really does fluctuate from really hot to really cold, that it might be more necessary here. But because of other related phenomenon, I mean, I'm still going to do it. I mean, I mentioned creep. Do y'all know what I mean when I say creep? Did you hear about that in materials? It's not. I'm not talking about the one song by Radiohead. My goodness. And seriously, so was that mentioned in materials? Creep is continuing deformation under the same amount of load. And it violates principles of mechanics of deformable bodies, but it happens, okay? It happens in materials like concrete where the properties change over time. It's something you really can't avoid. I mean, concrete in many ways is an active material. Its properties today and its properties tomorrow are different. You know, and you all know that from civil engineering materials. But I'm saying after 28 days, it's really nothing you can do about that. Yes, sir.
What you're all talking about, would that only matter up front, like say the first month, and after that would not matter?
Well, concrete tends to experience its highest rate of maturity over that period of 28 days. It does, but it also loses its durability over its lifetime too. So he's right. I mean, concrete's FC prime will creep up, no pun intended, throughout its design life. But its durability and its ductility will go down. And think if ductility goes down, its susceptibility for cracking will go up, you know. I mean, if I ask you to picture in your head, like an old sidewalk, one that's like 10, 20, 30, 40 years old, first thing that pops in your head is it's cracked all over the place, right? The loads arguably didn't change, but it did, you know. Does that make sense?
What about a pile cap? Like, that's something you don't want to, anything to happen to that.
Well, all right, no, you're right. Pile caps and foundations are designed a little differently. Your cover requirements are different. They're arguably going to be thicker because they're experiencing larger loads. Well, the load's ultimately going to them. Yeah. You've got a lot of punching shear aspects and bearing capacity aspects that you got to consider there too, and cover. So, yeah. All right, I need a number for this. What do I have? Okay, so is that an accurate representation? Do I have a second on that? All right. All right. Now, to compute required steel areas. All right, computing required steel areas. All right, so we've got main reinforcement. All right, excuse me. All right, main reinforcement, let's see, we're going to go with AS required is what we've been computing, rho BD. So rho B is what? There we go. Everybody's paying attention. And what's D? 5. Now, what do we have here? checking this out. Depth of the stress block. That's A. Would you, okay. You have to do that when you're going and validating the capacity at the end. I mean, we have to have a design to check. You see what I mean? What do we have here? 0.236. Now, let me be clear, okay? This is 0.236 square inches, but this is how much steel we need per foot of slab. Does that make sense? In other words, that's how much steel we need in that given strip, and then we're going to repeat it as we go down the slab. Now that's for main steel. For temperature steel, or shrinkage and all that other stuff, we have AT required, and this is a constant. It's 0.0018 BH. Okay, it's not D, it's H. Okay, that's not a typo. That's going off the spec. Okay, so that is 0.0018, 12, 6. All right, so what do we got? 0.129, 130. I got a second on that? All right. Is everybody okay with that? All right. Okay, so does everybody have everything they need on this panel? Okay, all right. Then let me do this. Okay, let's select some reinforcement, but in order to do that, I need to calculate some maximum spacings. In other words, let's say I had a really economical choice of rebar, and I could say, all right, let's use number 11 bars, but let's space them at like 30 inches. Hey, we'll save money on the steel. Do you really think that a slab is going to behave the way you want it to if your rebar is spaced like 30 inches? You're going to have a massive area where there's just no rebar. So you have to have at least some semblance of rebar spaced evenly throughout the slab, and that's what we're doing here when we calculate S max, or maximum spacings. So maximum spacing for, well, here, let me do this. Let me write this. For main steel, S max is the minimum of 3H and 18 inches, which is the minimum of 3 times 6 inches, or 18, which, heck, that's just 18 inches. I swear, when this pen gets closer to the top of the screen, it gets choppier. All right. For temperature steel, it's the minimum of 5H and 18 inches, which I don't even need to do any math. I can tell you that's 18 inches. So my point is that for this particular slab, I don't care what rebar pattern we pick, we cannot use a spacing larger than 18 inches. I mean, fortunately, our beam design aid doesn't report spacing larger than 18, so that makes our life a little easier, but it's something you need to go through and check. On this slab, it's 18. Maybe it's not on the next one. Okay? Does that make sense? Okay. Now, okay. Now let's take the, let's start off with the main steel. So what is the area required for the main steel? 0.236, okay? So I'm going to sort of borrow yours a little bit. So let's look at bar numbers and let's see 0.236. What is a good option for number 3 bars, let's say? Like if we had number 3 bars, how far apart could we space them and it works? Five and a half inches. Do I have a second on that? Everybody see that? So I could use number 3 bars spaced at 5.5 inches, and that would work. Now what's the area on that? All right, what about number 4s? Is there a good viable option there? Somebody else, or back here. Anybody see a good spacing there? 10 inches. Now, why did you pick that? What's the area? 0.24. Ooh, interesting. Now we have 2 options that have the same amount of area. Now, if you're the designer, which one would you pick, the number 3s or the number 4s? Well, if we're, now, hold on. If we're buying based off of pounds of steel off tonnage, then they're going to be the same price because it's the same amount of steel. Now let me ask you the question again. If you were the designer, which one would you use, the number 3s or the number 4s? You're saying number 3s, you're saying number 4s. Let me ask you, why are you saying number 4s?
Because since they're spaced out.
So you're going to need less of them. Less bars to handle means less bars that need to be placed, which means less labor that needs to be incurred to place those bars. Less cost. Did you have a question?
No.
Somebody raise their hand. No, somebody raise their hand.
I have a question, but
No. What is it?
do you have to deal with like slab curling and slabs?
What's that?
Like when we were in materials, that's what saw as like a main drop of concrete, which is 400 slab. It's curved. So you have to deal with that when you're talking about.
You talking about slab on grade or just slabs in a building?
Slabs in general, he was saying it was curled, like due to like the properties of concrete and drying because of heat.
Well,
And he was showing us like examples of where it's like curled in massive structures with different properties.
but are we talking about slabs on grade?
No, they were on like flat ground.
That's what I mean by slabs on grade. I mean they're being poured on the ground. I'm talking about a floor slab in a building where the ground is not acting like a big heat sink. You see what I mean? We're talking about an elevated slab in a building. I'd argue that's not really a big concern if you're talking about the slab on the 40th story of a building. Now, let me also say this. You do have to account when you're detailing the rest of the structure for the self-weight of the slab. In other words, there's a technique that we use in a lot of structures called cambering. Have you ever heard of cambering? Anybody ever heard of that? So if you don't know what cambering is, the idea is this. When I take a floor beam, right, and I put it in the building, it's actually bent upwards slightly. In other words, whether it's concrete, they cast it upwards, or whether it's steel, they actually physically, in the fabrication plant, will bend it permanently so that it's got a little bit of an upward curve to it. The idea is you frame it into the structure, and then you pour your concrete. Now, that concrete's heavy for your slab. It deflects downward. But the idea is you bend it upward that perfect amount so that when you pour the concrete, it deflects downward and it sits flat. That's called cambering. You bend the structure upward for the dead load so that when you place the dead load, it sits flat. But we're not talking about slabs on grade. We're not talking about slabs that are poured on the floor. I mean, think about this. Think about this. So, see this picture? The slab is supported between 2 beams. It's not on the ground. You see what I mean?
I just didn't know if it had the same effect or not.
No. The big thing to concern yourself with is that the slab isn't sagging too much under its own self-weight in a situation like this. I know what you're talking about with that, but that's more, I'd say that's more of an issue with slabs that are on grade and have issues with heat loss. Everything's pretty open in a situation like this. So if it's going to be experiencing heat loss, by and large, it would be experiencing at the same rate. You see what I mean? Does that make sense? Everybody else okay with that? Are there any other questions? This is good stuff.
I got one.
Yeah.
Could you go back to the original slide?
Slide?
Yeah.
You mean this?
No. Sorry. No problem. Why is it 0.24 inches square inches per foot?
Is that not what the table lists? No, that's the beam design chart. I'm looking at the other one. The one you're looking at here, that's the one for the beam design. There's another. Yeah, there's another one. There's another one like this one. This is for slabs.
Oh, okay.
Is everybody else finding that 0.24? No, the number 4s. It's the same amount of steel, and ultimately, if I was buying, per tonnage, I'd be spending the same amount of money. But the second option, that's literally fewer bars. So it's fewer bars to handle, fewer bars that need placed, fewer bars that need tied in. It's going to be less labor down the line. Does that make sense? Now, another point, it's not the difference between number 3s and number 14s. It's the difference between number 3s and number 4s. So you could say, well, what if you pick something like number 14s? Well, number 14s are really, really heavy and they're harder to handle. Number 3s versus number 4s, I don't know that there's a big difference in terms of like workers handling them. I mean, they're a little heavier, but not terribly. Does that make sense? All right. Are there any other options that are 0.24 square inches? So really, if I'm going to pick, these are the two ones I'm going to pick off of, and I'm going to pick based off of this. All right. What about temperature steel? What was the required amount of steel for temperature? 0.13. What's the option that I should use? You all tell me. 0.13 square inches per foot. Number 3 spaced at 10 inches, right? Right? Okay, so you picked that because it's an area of what? Does that sound good? All right. So I propose to you that the trial design for this slab looks something like this. All right. So here's the slab, and I'm going to blow the slab up a little bit so everybody can see what's going on. All right. So there's the slab. There's that. And there's that. So those are the two beams going in and out of the page, and the spacing between those beams is about 10 feet. Okay, does that make sense? All right, so the thickness for this slab is about 6 inches. So it is 6 inches. This is 6 inches. Okay. Now the main steel, the number 4s at 10 inches, okay, they're going this way, okay? Because think, if this is bending, it's bending like this, right? So you need that main steel to resist that bending in this fashion. So the bars that are going this way those are number 4s at 10 inches, okay? So there's going to be a number 4, bless you, there's going to be a number 4 here, then a number 4 here, and then a number 4 here, and a number 4 here. They're going this way, in and out of the screen, right? Now that's the main steel. The temperature steel, we also need steel going this way, okay? So the temperature steel, typically what you do is this. We're going to have something like that, something like that. It's just going to sort of go like this. You don't have to draw as many as I am to get the picture. So these are the number 3s spaced at 10 inches, going in and out of the screen. Does that make sense? So think, when I place load onto this slab, it's going to want to deform like this. So these red bars, these number 4s, those are the ones that are primarily picking up that resistance due to bending, okay? But the blue bars, the ones going in and out of the screen, we need some there because we also need to resist that potential cracking due to changes in temperature, shrinkage, creep, things like that. All right? Make sense? Again, we're taking that rebar and placing it on the bottom because that's the region of the slab that's going to be experiencing tension. All right? Make sense? Yes, sir? You can if you want. The big thing is just make sure you're indicating which is the main steel, which is the reinforcing steel. But yeah, you're more than welcome to do that. You can also get fancy with it if you want and, do this. So, you're going to have red bars, going like this, and you're going to have the blue bars doing that, etc. Does that make sense? Everybody else okay with that? Everybody good? Okay, now here's I'll say the crux, or here's the issue with this calculation, and that is we're making sort of maybe a little bit of an odd assumption with this. We're assuming that you've got the slab and the beam, and they're just sort of sitting on top of one another. Now, in a steel structure, yeah, that's the case. You might have some shear studs to lock that slab compositely with the beam, but in the end, it really is a concrete slab sitting on top of a steel beam. But it's possible in a concrete structure that that's not the case. What's possible in a concrete structure is that you get something like this. Okay? Now this is a little different. Okay? This is an instance where the slab and the beam have been cast integrally together. Okay? So it's one continuous floor system. There's some serious advantages to this because if you're looking at the beams, you can count on a portion of that slab as being effective in resisting load for those moments, and we call that a T-beam. Okay? All right? T-beams, if you can count on that monolithic construction, you can get a significant advantage in capacity for that beam, and ultimately, you might be able to take that beam that was 24 inches deep and maybe make it 20 inches deep because you got part of that slab working for you. Okay, does that make sense? And so I guess the official name would be looking at a flange section, a concrete section that has a significant upper flange. Now we can have either T-beams or L-beams, and by L-beams I just mean, well, imagine you've got the end of the floor system. Let's say it sort of gets cut off right here, so this particular beam, now that's an L-shaped beam. All right, you see what I mean by that? Mostly, more often than not, we're going to be looking at T-beams, though. Okay. Sound good? Well, no, I guess it doesn't, but for a T to not be symmetric, your beams would not be spaced evenly. In other words, to give you an example, let's say I've got beams supporting this floor system, right? And let's say I've got a beam right here, I got a beam right here, then I got a beam all the way over here. Well, that middle beam's going to have a different flange width on either side, right? But that's sort of an odd way of framing out the structure. You see what I mean? I mean, more often than not, we're going to want to try and keep our beam spacings rather even. You see what I mean? Remember that picture of the third floor parking garage? Remember the T-beams were pretty evenly spaced. We didn't really want one set that was close together and then one that was apart. It really wouldn't lead to an efficient design anyways. Does that make sense? It can happen, though. It can happen. On the exterior girders on bridges, that does happen, and you just literally take your tributary width and go with it.
So if you have the option to use a T-beam, like comparing the view if you look at it, why would you use a double angle?
A double angle.
Like how we have double angle, if you can
Availability. Maybe, well, keep in mind, I mean, you might not have T-sections available. This is a structural steel question. This isn't a concrete. Yeah, let's be clear. You're talking about specifically something in steel, not in concrete. But what I'll say is this. Angles are simple, and they're readily available. P sections might not be available. That's point one. But if they are available, you might want to go with the WT, because if you've got two angles, you have to connect them together, and that's more labor. So it's a trade-off. So, but honestly, for beam sections, you're primarily going to go with an I shape anyways. So, yeah. Everybody okay with this? Everybody good? All right. Now, here's the thing. So, I heard something. Okay. If it was Siri or something, I don't know. All right. So, here's what's going on, and I want to be clear upon this. What we're going to be doing is this. We're going to be looking at a floor system that kind of looks something like this. And we're going to be asking ourselves how much of that slab is effective in helping the beam resist load. Okay? And we call that the effective flange width. Okay? Make sense? Now, this picture, I got to be honest, I think this is a little deceptive. Okay? And it's deceptive because the way that this is drawn out, it almost looks like we're using the tributary width, right? We're going halfway over, and that's our slab, right? That is not always the case, okay? Don't get me wrong, most of the time in bridge structures we do use the tributary width, but in building structures we're really not allowed to do so, and here's why. So what I'm looking at is what I'm looking at is the bending stress in a slab as you get away from the beam. So this line that's sort of curving down like that, everybody kind of see this? That line is essentially sigma equals my over I, but in sort of a, I guess, a more realistic fashion. This is that the stresses in that slab plotted as you get further and further away from the slab. And if you think about it, it kind of makes sense. Like if I got a beam spanning from here to here, and I'm stepping on the beam, I mean, yeah, I'm going to get a fair amount of stress in the beam, and I'm going to get a fair amount of stress in the slab portion. But if I start, looking farther and farther away from that beam, that slab is seeing less and less load. Does that make sense? I mean, I'm not saying it's not going to see any. I'm just saying if I'm standing right there on the beam, the slab that's all the way down there really isn't seeing very much stress. The closer you get to the beam, the more stress that you see. What I'm trying to do is I'm trying to isolate a certain portion, if you will, a certain portion of that slab that I can say, all right, the amount of force that's in this slab is about equal to what's going on everywhere else. So in some cases, yeah, tributary width works, but sometimes it's not that simple. So in ACI, they offer us a pretty simple approximation, if you will, for determining the effective flange width for a T-beam or for an L-beam. That's the beams on the side. So that effective flange width, in other words, this dimension right here, we compute that as for T-beams being the minimum of the following quantities. So L over 4, so if the beam was 30 foot long, we take that and cut it in 4, so 7.5 feet. That could be our tributary, or that could be our effective flange width. We can take the web width and add 16 times H sub F. H sub F is just the thickness of the flange, or the girder spacing. Now that one on the bottom, the girder spacing, that would be the tributary width. So it's possible that it works, but in many cases it doesn't. For L beams, the calculations are pretty similar. It's just different constants because you're looking at the beam on the end, not the ones that are in the middle. Sound good? Okay. Now here's that's simple, and I'm right. When I say that's simple, I'm talking about your considerations on things like homework problems, exam problems, and really the concept. What gets complicated is this. Okay. So what I've got here is a T-beam, and I'm looking at the same T-beam from two different contexts. Okay. So let's take a look at the image up top. So I've got an area of steel on the bottom. I've got a web width. I've got a flange thickness, depth, etc. Okay. Now this shaded portion right here is the stress block, right? Remember, how do you determine the depth of that stress block, right? You determine the depth of that stress block such that C equals T. Everybody remember that? Okay. This is where I think you sort of got to make sure that you're paying attention, because I'd argue that the actual mechanics of concrete design, this is when it starts to get a little tricky. This is when it starts to get a little complicated. All right, so C equals T. So I say my tensile force is the area of steel times Fy, and then my compressive force is whatever the area times 0.85 Fc prime of that is, and then I solve for A. Make sense? Now, let's say, just to throw some numbers in, let's say I do that and I have a flange thickness of 3 inches, so this is 3 inches, and I calculate an A value of something like 2 inches. Okay? This would be an example of what I'm calling a rectangular T-beam. Okay? Now, when I say rectangular T-beam, what I mean is it's a T-beam, but the stress block is rectangular. It's just a rectangle. My question is, if I was trying to compute the moment capacity of the upper section, the one that you see up top, how is that any different from the moment capacity of, I'm going back a little bit, I know, but how is that moment capacity any different than the moment capacity of this? Okay? I know I went way back, but I really want you to think about this. I want to look at this beam. Okay? This beam is a rectangular beam. Its stress block is rectangular, right? It's got some width B and some depth A, right? And its moment capacity is ASFY times D minus A over 2. Is everybody with me on that? How's the moment capacity for this any different than the moment capacity? Come on. How's that any different than the moment capacity for this one? We have an area of steel times Fy on the bottom, and on the top we have a rectangular stress block. Okay? So to calculate the moment capacity of this one, it literally is just ASFY D minus A over 2. But if I've got this one, this scenario, it's a little different. Because my stress block is not rectangular. Okay? My stress block is T-shaped. All right? So you can't just say force times moment arm and that's it, because what's my moment arm for this shape right here? You could sort of say, oh, you got to go through and compute centroids and things like that. Don't worry, I've got, I think, a simpler way of going about this. Does that make sense? Everybody okay with that? The point is that there is a difference between what we're calling a rectangular T-beam and a true T-beam. A rectangular T-beam has a stress block that is, in fact, rectangular. A true T-beam has a stress block that is T-shaped, okay? And that's when you got to sort of roll up your sleeves and make sure that you're doing equilibrium and doing your moment calcs right. Sound good? No, that's something we have to determine. And there's a way that we can go about that. Okay, now let me see what time it is. All right, so we're running out of time, so I'm going to do that next time. But let me sort of explain what's going on. So I've got 2 examples, 9A and 9B. Okay, now these are both representative T-shaped beams. And what we're going to do is we're going to compute the moment capacity for both of them. Okay? What we're going to find is that the moment capacity for one of them is going to be reflective of a rectangular T-beam, and one of them is going to be a true T-beam. And I think you'll understand when you go through the math how that's going to work. The long and short of it is this. So, and I'll get to your question here in a sec. So we've got a stress block here, right? Now this flange thickness is what, 4 inches? So if I calculate the stress block, like just assuming it's rectangular, and I get a stress block that's 7 inches, well then it would mean that my original assumption isn't correct, because I can't have the stress block go all the way down here if I've only got 4 inches. So that would be an instance of a true T-beam. If it came out to be 1.6 inches, then I'm in rectangular territory.
So the only way we figure it out is by just trying.
Exactly right. Yes, sir?
How come you only have steel in that one flange? Why would you have steel in the upper part where the opposite people is?
Okay, to answer your question, we do consider doubly reinforced beams where we have steel up top. We will do that later, okay? Like later on here, I'll skip ahead a little bit. I mean, we have doubly reinforced beams where we have steel up top, okay? And you can consider it, okay? But it's one of those you got to walk before you can run type things, so we will get to it. I promise. But let me also say, steel in compression is there, but it is certainly not as effective as steel in tension. Because think about it like this, okay? So you've got concrete in compression, it can handle a lot of compressive stress. I mean, you can throw some steel up there, but that concrete's going to be doing the majority of the work. Really, where you need steel is steel in tension. I'm not saying there isn't steel in compression there. I'm just saying we don't really need to worry about it right now. Does that make sense? Everybody else okay with this? So to be clear, we have moved the exam to Friday. Homework's still due on Monday, though. We're still doing that. All right. What? All right, let me stop this real quick.